Welcome back to Innovation Garage. Here I am with Artur K, and we want to start off this video series by giving you a demo of what he's been working on. Tremendous amount of work, and he's done all the heavy lifting. And I was here to provide him with essentially a test mule, and we want to talk about his invention here, which is a shield for the Arduino DUI, a common platform. So we'll start off the video with a simple demo of the gauges. These are OEM like aftermarket gauges for a Chevy truck, a GM gauges essentially. You want to go ahead and do the honors. It controls 5 of the 6 gauges. Obviously there's 6 on the dashboard. The one that is just a standard connection is the voltmeter essentially. This device controls temperature, oil pressure, fuel or state of charge, and RPM and miles per hour, the speedometer. Here is the man behind the device, Artur. I'll go ahead and turn it over to you so you can start telling us about why we came up with this, why you came up with it, and basically walk us through some of these gauges and then move on to the more advanced and other features of this.
Yeah, absolutely. So we needed some way to control those gauges, and these are aftermarket but OEM style gauges. So that means they use standard sensors and standard signals that you may find in a regular gas-powered vehicle. For example, talking about temperature, you have a standard temperature sensors, thermistors, and they are basically installed in usually in a block of the engine or some other component, and they basically serve as a current sink for a gauge. So in order to be able to control those gauges, here we needed some very simple sync circuit that would drive those gauges. It would be controllable by our microcontroller. So we built 3 of those circuits here on this board for the gauges that Greg just mentioned. The fuel, oil pressure, and the temperature, they all work the same way. There's just some small fine tuning for a specific gauge, but the principle is the same. So in this cluster we have 2 types of gauges. Some are analog gauges like temperature gauge, fuel gauge, and oil pressure. They basically receive signal from so-called senders, and senders are usually in the form of a thermistor, which is basically shorting to the ground through the gauge and serving as a current sink for the gauge. The other type of gauge that we have here is speedometer and tachometer, and those work on a little bit different principle. They basically analyze the waveform like a square wave, or not exactly perfect, but waveform that is being captured from ignition coil, for example, and basically measures the frequency of the signal and translates into proper RPM, and a similar principle with speedometer. Obviously we have some kind of sender that sends electrical impulses, and the frequencies are measured and translated into the speed of the vehicle. So for that we have a special driver circuits on a board that basically produced a square wave of a certain frequency and that correspond to either RPM or speed of the vehicle. Okay, so to summarize, we have a couple of dedicated circuits on this board to drive the gauges. The major ones being three current sinks that can be configured to work with analog gauges, and then we have a couple of PWM drivers that are being used to drive speedometer and tachometer. So that's the main functionality, but we wanted to add some extra stuff to the board because who knows what Greg is going to come up with and what else he wants to put in the car and control. So therefore we added two extra PWM outputs that can be set up for different actually voltage of PWM square wave. Most of the devices that you may find in a motor vehicle industry will be powered by 12 volt, and they will require 12 volt square wave PWM to be controlled, but there are some that either require 5 volt or 5 volt is necessary, so those two extra PWM can be set up to either 5 volt peak to peak or 12 volt, so that's a nice feature. For example, the Tesla pump, I know natively it uses 5 volt square wave. It might accept 12 volt as well, but I have not experimented with that. In addition to those PWM drivers, we also built in a couple of digital inputs, general purpose digital inputs, and two analog inputs that could be used for various analog signals, including temperature sensors, for example. Another feature is we wanted to give it some ability to control power for certain devices, so there's two low side switches built in and one high side switch for 12 volt devices. Another major feature is, as you may be aware of, Arduino DUI board does not have a EEPROM memory, so we added a chip here, so you can basically store all the necessary settings. So this is like one of the missing feature and capability of DUI, which we added here. And so perhaps the last feature would be the CAN communication. So there's two CAN bus transceivers here, so we have two CAN bus channels available for this board. So we talked a little bit about the circuitry that is required to control those analog and somewhat digital gauges here, and about some other additional functionality that the board has, but also interfacing with other controllers. It's very important because once we are able to drive those gauges, we need to actually get the information to display on the gauges. So we wanted this to be independent component. So basically all the main signals that are being displayed on the cluster gauge, they come through CAN bus. So as I mentioned, we have two CAN bus channels here, and one of those channels is basically talking to the rest of the car. In our case, it's on the same bus as a VCU and as a safety box, or you may have a ISA shunt or some other component such as charger or DC-DC converter. So basically all the essential signals we pretty much receive from the VCU. We're getting RPMs of MG2 and knowing the gearing ratio, we calculate the speed of the vehicle. We are also receiving temperature information from VCU. It's in our case we use inverter temperature, and as a pressure gauge we are showing PWM settings for transmission. Oil pump is going to be driven with some dynamic settings. We're going to base it based on the torque required to basically be able to see what the demand on the pump is. So another important gauge that we have here is the fuel gauge. So there's a couple of options how it can be used. So this is being standard gauge. It basically shows the originally fuel level from 0% to 100, actually 99 because it only has 2 digits in our case. So we were trying to come up with ideas how to best utilize this, and ideally we would like to show the proper state of charge on this gauge from between 0 and 99 or 100%. However, we have a little challenge here at the moment, since Greg is using safety box, the BMW safety box with its built-in internal shunt, and we can get certain information such as voltage and amps, but we don't have information regarding kilowatt hours, so that would be essential to properly show the state of charge. So for now we are doing some implementing some workaround, and Greg during his testing likes to go by the voltage of the battery, which is kind of difficult to translate into state of charge, but it gives you some good indication. Since this gauge only has 2 digits, we decided to basically show the voltage between 300 and 400 volts. That covers most of the useful range of the battery. So basically we have a gauge that's showing 50, that means 350 volts. So I think we talked enough about the gauges, but also I wanted to mention a couple of other use cases for this board, since it has some additional circuitry and drivers, and it could be used for controlling different types of devices. So for example, it can be used to control PWM controlled cooling pump. In our case here we use Tesla cooling pump, which is PWM controlled. So until now Greg used a dedicated little Arduino Uno board to be able to control this pump, and now having this board he can retire Arduino Uno, and we can add, we actually have done this already, we implemented PWM control for the cooling pump. This can also control other devices such as the radiator fan. I'm actually using similar in my project from a BMW X1 PWM control pan. It works really great. We can also control AC compressor, and actually this board can be used to implement all the controls for climate control of AC, since we can control fans, and we can also control the compressor, and we can also connect the temperature sensors that might be required to figure out the proper duties for PWM for the compressor and the fan based on the internal or external temperature. So in addition to those, also since we have 2 CAN bus channels, currently we are not using one, but if Additional, maybe isolated, dedicated channel is needed to control some devices. Maybe you can have a device that runs on a different with a different baud rate, different rate. It could be used for that purpose, or if there is a need to perform some translation and bridging between different CAN buses, this could also be facilitated by this board and appropriate software.
So we've reached the put the expert on the spot segment of our show, and I'm going to ask Artur a few questions that are kind of running through my mind that maybe you would share with me. And one of the questions I have is, why can't we just take the signal from the tail shaft of this Lexus GS450H transmission, the speedo sender, if you will, and just connect it to a speedometer, or connected to the tachometer. So can you tell us, guys like me who don't have electronic engineering backgrounds, why we can't just do that, and why going through a shield like this is the clever way to do it?
Sure. I mean, this is another alternative way to possibly capture the speed of the drive shaft, but this would require some specialized circuitry amplifier that would amplify a signal from the sender that is built in Lexus transmission, and would have to be converted into the level that could be then basically recognized by the Arduino, but it would also require some processing, so that this kind of overcomplicates this solution. So much easier solution is basically getting the digital information that is available from the Lexus inverter, because we know exactly this parameter, and we can directly use it, or with manipulating this certain amount of simple manipulation to account for gearing ratio and stuff like that.
So my next question is, for guys considering breathing new life into classic cars, vintage cars, my truck originally didn't have digital gauges. It had these needle, gauges. And so would your design, would this type of solution work with those old kind of gauges where they just have the needles?
Yeah, absolutely. So the gauges we are dealing here with, they appear to be digital gauges because they have digits, numbers on them. But as I mentioned, these are OEM style gauges. So what I mean by this is that they use common signals that are found pretty much in all of the vehicles throughout the industry, using the common senders for temperature, for RPM, for speed, and they basically work on the same principle. So even though we have those digital aftermarket gauges here, this controller would actually work perfectly fine with most of the OEM gauges that the older vehicle may be equipped with. So it's definitely not necessary for the newer vehicles that entire cluster is pretty much controlled by the CAN bus signals, but the older vehicles such as this one, maybe going back 15-20 years back, will most likely have those analog style of gauges, and that controller can easily work with those.
I've been through this process with you, but for somebody interested in this type of solution, I mean, is it just a hardware solution, where we take an Arduino DUI, slap on the shield on top of it, or is there a bit of code you need to seed or install on your VCU? I happen to use the Lexus. Sorry, this is a long-winded question, but I have the Lexus VCU from EV BMW. But what if you have a Nissan Leaf? What if you have a Prius? What do you have a different type of VCU? How do you integrate beyond the hardware?
Absolutely, very good question. So we wanted this controller to be versatile and work in all kinds of scenarios. And really, the most common way of communicating between those components is through CAN bus. And we talked about this a little bit, and even talking about old vehicles such as this one, we are introducing CAN bus as a part of our EV build, and most of the information that we want to communicate to this board is available through CAN bus. So there's obviously a little bit of Arduino code that we had to develop to process the information received through the CAN bus, and it may require a little bit of work of to extract the information from the sending device. So basically, we just basically expanded a little bit, updated the code for VCU to send the information that we needed to be sent over the CAN bus to process, like for example, those temperatures that we use, and RPMs and other parameters. So that's pretty simple stuff. But most of those information is being sent directly through some OEM components, like for example the Nissan Leaf inverter and other CAN controlled inverters. Usually that information can be easily extracted from the stream.
So to build on this question and this CAN bus network, does running gauges, could these types of custom gauges over CAN, require its separate CAN connections and CAN network? Because we have limitations on the VCU. It comes with CAN 0 and CAN 1. So can it share a CAN channel, if you will, with other devices?
Yes, absolutely. CAN bus system, it allows for quite a high throughput, and it's kind of busy, but it handles quite a lot of information being sent, and is designed specially to share information between multiple devices. Obviously, all the modern cars have many components on the same bus, and they communicate without any problems. The CAN bus system has a special features built in to detect collisions and make sure that the data is not being corrupted. So it can be put on the same CAN bus with other devices, like for example in our case I mentioned, it's on the same bus with the VCU, with the charger, with the DC-DC converter, and a safety box, and there's no problem. But since we have this second CAN bus channel available, it could be used for other purpose, for isolation from different CAN bus.
So in terms of compatibility, I think the one requirement I know of, and I'm not a CAN bus expert, is something called CAN bus speed or baud rate, something like that. What rate do these gauges run on? Is that flexible? Can it be adjusted to meet the speed or match the speed of an existing device that somebody may already have?
Yeah, so there's a couple of common speeds that you may find in vehicles and projects. The most common is 500 kilobits, and this is what we're using for now.
Thanks, Artur. This is an ongoing project. We just spent a number of days road testing, having a lot of fun with this, a lot of challenges, and a lot of really clever solutions that this man came up with. But we'd like to hear from you guys, and if you'll be interested in something like this, and also ideas you may have, other gauges you would want to implement it, and yeah, thanks a lot, guys.